we are going to tackle how to maximize and or minimize some functions, specifically some continuous functions. So basically, if we're maximizing or minimizing continuous functions, we have really two scenarios. We're going to talk about them over closed intervals. Closed intervals, closed finite intervals, or open infinite intervals. So basically, that's this. If I give you a continuous function, will it have an absolute maximum? Will it have an absolute minimum? And how can you apply that to real life? We're talking about cost. If you're a business, you probably want to find out the lowest cost, right? Or you want to find out the maximum profit. That's probably what you want to do, right? You want to find the maximum cost and the minimum profit. That would suck, because then you're going to waste a lot of money and you're going to get fired probably. Or if you just guess, you're not going to be making as much money. You're going to be spending too much money if you just guess at things. I think if we produce this amount, then it's going to be good. Let's try. Well, why don't you do the calculus and figure out exactly what you need to produce, exactly how much it's going to cost, and minimize the cost, maximize the profit, and that's pretty much the idea. Does that make sense? If you're making stuff, you want and you're trying to, like, boxes, are you going to make a storage box that's this long and this wide and that deep? Would that be a good storage box? Not if you want to maximize the volume, right? With the same amount of surface space. So if I say, here's 1,000 square feet of cardboard, make me the best box you can. We should be able to do that. We should be able to figure out the dimensions using some calculus. And that's what we're talking about, maximization problems. Well, I'm going to relate this back to absolute max and absolute min. Here's the idea. If you have a closed interval looks like this with brackets. If you have a closed interval with brackets, do you for certain have an absolute max?
Yes.
Absolutely. Do you have an absolute min?
Yes.
So for a closed interval, because these have brackets, you will certainly have solutions. There will be solutions. If it's a continuous function and there's a closed interval, always. How about open? Open intervals. Because remember with absolute max and absolute min, if you think back, if you watched the video from a while back, absolute maxima and minima must occur at one of two places. Must occur at relative max or min for continuous functions, relative max or min, or at endpoints. Do you remember talking about that? If I take away the fact that it has endpoints, well then it must occur at relative maxes or mins, which don't have to be, could be, but don't have to be the absolute max or min. So while a closed interval will definitely have an absolute max or min, or will definitely have a maximum and a minimum, because we have endpoints, this one might not have them, because there's no endpoints. Are you with me on this? So it might not have solutions. Well, we're going to jump right into it with an example. We'll start off quite simply. I want to basically do this example to give you some vocabulary and how to do the problem. Let's say that I want you to build a region that's fenced in. So basically a rectangular region. So basically Wyoming or something. I think it's pretty much a rectangle, right? Well, if you consider the Earth to be flat, it would be a rectangle. If it's curved, well, never mind. It's a surface space. But let's pretend the world's flat for Wyoming, because have you been to Wyoming? It pretty much is. Not really, they have mountains and stuff. But let's just pretend it's flat and it's a rectangle. I want you to fence it. We're going to make this easier than that. But basically you're fencing a rectangular region. Yeah. Fence a rectangular region and maximize the area. you have 100 feet of fencing available. Of course, this is not Wyoming anymore, okay? But because Wyoming is very large, we're just going to fence some regular area, okay? And you have 100 feet of fence. This, by the way, is called something specific for these applied problems. It's called a constraint. It says this is what you have to work with. It's putting a limit on your area, basically. Because if I said maximize the area, you just go, okay, I'm going to make it as long as I can times as wide as I can. That's maximizing. But if as soon as I say, oh, you only have 100 feet of fencing, well, that changes things, doesn't it? You have to have that statement. That's called a constraint. Constraints can be given to you. They can be implied in the problem. They can be realistic constraints. But somewhere in most of these problems, you will have some sort of a constraint. Now, one great thing to do with these applied problems, they're all going to have something you can draw. So try to draw a picture of them to get your mind wrapped around it. We're talking about a rectangle here. So we're probably going to want to draw a rectangle here. So let's draw a rectangle here. It doesn't matter what you call the sides, but call them something. Call this one maybe X and this one Y. Bless you. You with me still? What's this side?
X.
And this one's Y because inherently we know about rectangles. Opposing sides are of equal value. So we have that. The next thing you do, you come up with some sort of area that has to deal with what you're trying to maximize or minimize. Something you're trying to find the maximum or minimum of. Very much like with related rates, right? You're trying to find an area that incorporates everything. Here you're trying to find a formula that incorporates everything. Here you're trying to find a formula that incorporates what you're trying to maximize with your figure. So we want our formula. And you need to list out any constraints that you have. Okay, tell me something. We've already drawn our picture. Let's come up with a formula that has to do with what we're trying to maximize. What are we trying to maximize here, ladies and gentlemen? Okay, so if we're trying to maximize area, you need to be able to come up with a formula for the area. What's the formula for area? Specifically for this, what's the formula for our area? XY would give us the area of that rectangle. True? X times Y. Now let's talk about our constraint. What does the 100 feet of fence have to do with anything?
That has to be your,
What's that called?
the domain of the function.
Oh, kind of, sort of.
Perimeter.
Perimeter. We'll talk about domain in a minute, okay? But the 100 feet of fencing, you know that goes around your figure, right? So that is your perimeter. So right here, our formula we're trying to maximize is the area. You with me on that? That's what the question says. But a formula that's inherent in our problem has to do with our constraint. And it says, well, I know that if I add up all the sides, it has to equal how much? 100. Now, add up all the sides. How much do you get?
2x.
Good. If I add that up, I add this one, this one, this one, this one. That's 2 x's plus 2 y's. And you get another formula out of your constraint. Raise your hand if you feel okay with this so far. Okay, very good. Now, the question is, what are we trying, here's where you answer your question if you have two more than one formula. What are you trying to do here? Are you trying to maximize your constraint or maximize your area? Your area. So what you're going to do, use your constraint, solve for one variable, and substitute it into the formula that you're trying to maximize or minimize. The reason is, can you find a derivative of x and y? Yeah, you can with implicit. However, you're going to need to solve for y anyway to be able to do anything with it. So solve this for y and substitute it in. So we're going to solve our constraint for one variable. I would choose y. Just, I don't know, I like y. So solve for y and then substitute that into your formula. So you're going to solve the constraint. For one variable. And sub into your formula. Okay, you get to choose which one you want to solve it for. I'm going to choose to solve for y. So I'm going to subtract 2x, I'm going to divide by 2, and I'm going to get
50x minus x. Or 50 minus x, yeah, yeah.
okay.
50. That's right.
So from here,
Just 30x.
yeah, if I divide everything by 2, I'm going to get y equals 50 minus x. So far, so good? What that does is says, okay, now that I have y equals 50 minus x, let's take that, let's put it here. That changed our formula from 2 different variables into 1 variable, and that says I can do something with calculus with it. All right, you need that 1 variable for us. So I'm going to get a equals x, and instead of y, I need parentheses. Do you see why I need parentheses? Are you sure?
Yeah, you probably hate us right now.
Hate? No, hate's a strong word. But you need parentheses. They're important. If you give me this, you know I'm going to have a cow. Right? Literally, I used to live on a dairy. I could have a cow if I wanted. There's 6,000 of them. Yeah, 6,000 cows. There's only 45 of you. You have 45 cows.
5 cows for each person.
Yeah, a lot of cows for each person. So far, so good? Make it easier before you do the next thing we're going to do. You see, right now, we have this formula for area, right? What we're trying to do is maximize the area, which is why we're working with the formula for area. Now, what we learned here was that this really is a closed interval. There's only so far I can make my x. I can't make my x or my y like 3,000 feet, right? Because I only have 100 feet to work with. So I'm actually dealing with some domain restraints right there. We'll talk about that in a second. But we know that wherever a maximum or a minimum occurs, it's going to be at either an endpoint, which we'll talk about in a bit, or it's going to be at a relative extreme point, a relative max, like this. How do you find relative maxes? What do you do with functions? That's a function. What do you do with functions to find a relative max? You take a derivative, because you know relative maxes happen where the slope is 0, right? To find the slope, you take a derivative. So with your applied problems, let's take a derivative of that. Now, I wouldn't be so silly as to do a product rule here. I'd probably distribute and get $50x minus x squared and then take a derivative. But we're going to take a derivative because what a derivative is our, what's a derivative again? Slope. And we want to know where the slope equals 0, because where the slope equals 0 gives us a critical point, and that could potentially be our relative max or min. If it's a relative max, that means it could be our absolute max. If it's not, it will certainly occur at an endpoint, but it's something we need to check. So take our first derivative. That would be with respect to x in this case. Notice that if you had solved for x here and plugged in and had y's, you'd have dA dy. You follow me on that? Show your notation appropriately. This is with respect to the variable that you have, x. In our case, you get 50 minus 2x. Are you okay so far? What's that give you again?
Your slope.
Slope, and what do we want to find with the slope? Where it
Equals 0.
If it equals 0 somewhere, that's going to be possibly a change from increasing to decreasing. It might be decreasing to increasing, but it will give us the only point on our interval where that change could possibly occur. That's why we're going to check this with the endpoints later to determine whether it's an actual max, whether it's minimum. How much is x?
123.
Probably add 2x divided by 2.
Yeah, 25.
Probably 25. Hopefully 25.
Not 120. 25 something. I got the 25 right.
How many will feel okay getting x equals 25? Now, if x is 25, how much is y? Use your constraint to solve for that. Just plug in the 25. Y's gotta be 25. So if x is 25, we use this again. But then you're gonna have to check. You see, here's what we did. What we did is we found out that the only possible place where we have an absolute maximum other than the endpoints is right there. Would you agree with that? That's the only place that we change from increasing, decreasing, or decreasing, increasing. That's the only relative, even possible relative extreme that we have. And what we know from before is that absolute max, which is what we're trying to do, max or min, absolute max must occur at endpoints or at relative extrema. Our endpoints are, well, we'll talk about that. We're going to check right here. But our possible relative extrema is at x 25. Although there are some endpoints here. Can you tell me what's the biggest thing we could make x? Wait, 100? If you did 100, you'd have a one-sided fence.
99.
Not 99.
75.
Oh no, too big still. 50. 50. X could be 50. You have two x's, right?
That's right.
So if x is one thing, it has to be the other thing on the other side. If you do 75, you can't do 75, 25. That doesn't make sense. It's not a rectangle. Now, you might be thinking, well, is 50 and 50 a rectangle? Technically, yes, kind of. If you have 50 and 50, how much is y going to be? That's going to be a rectangle. Is that going to maximize your area? Actually, it has 0 area because it's 50 times 0, right? That would be 0. It'd be a line. You get just a fence next to a fence. But you could do it, right? So the maximum that x could be,
Farmer would be pissed.
like, you are the stupid, you may be.
It's for skinny cows.
Skinny cows come from California. Okay. So x is 50 equals the maximum value you can make x because 50 plus 50 equals 100. What's the least value you could make x? 0, because then y would be 50 and 50. Right? That'd be a straight line in the other direction. Again, your area would not be good. But here's the point. Okay, this is kind of a simplistic example, but it says this. It says if a maximum is going to occur, it occurs here, here, or here. It has to occur because this is a closed interval. It's going to be here, here, or here. So x is bound between, here's our endpoints. This says x is somewhere in the interval, that's what that little element says, somewhere in the interval of 0 to 50 inclusively. Including 0, including 50. That's somewhere where x is. If we have this interval, which is our inherent constraint in our problem, then our absolute max must be one of these three numbers. We know it's either endpoints or it's at a relative extrema. And that's the only place we could possibly have a relative extrema. Nudge if you feel okay with that so far. All right. So, you're going to plug them in. Where are you going to plug those in? First derivative is going to give you 0, because that's how you found that number. It's not the first derivative. What gives you values, people? The original function. In our case, that's our original function. Or if you have the y, you can plug it in there. That's okay. But plug it into here, and that's going to maybe be a little bit easier to do, I would say, for just x's. If you plug in 50, check it out. Look at, what's 50 minus 50? Your area is 0. We talked about that. That's a straight line this way, right? Plug in 0. 50 minus 0 is 50 times, gives you, that's the y equals 50 and 50. That would give, that's minimizing your area right there, 0 and 0. This one hopefully is maximized, hopefully it gives us something. Plug in 25. This said the area is 0. This said the area is 0. This said the area is We knew it had to be one of those three. This is the biggest one, ergo it must be your absolute maximum. So what do we say? The absolute maximum is 625 square feet when x equals 25. Basically, what shape do you have? You have a square. Yeah, you have a square. 25, 25, 25, 25, because x and y are both 25. So how you'd write it out, I really don't want to erase any of this, but I'll write it down here. The maximum area is 625 square feet, be specific. When x equals 25 and y equals 25. Feet. Do you feel okay with our example? Yes, no? We're going to go a little bit quicker now. We're going to, because we understand the idea. Formula, constraint, put them together. That's basically the idea. Let's talk about one that we've actually had before. If you want to go back and refresh your memory on the video, we had this problem. Excuse me, this problem, but we didn't do anything with it. Do you remember the problem where I said, I want you to take a piece of cardboard. I want you to cut sections out of it. I want you to make a box. Oh, it came out better this time. A lot better. Do you see the box? Good, I did my job. If I make this, what would I say, 16 and 30? Doesn't really matter, let's do 16 and 30. This is 16 inches. This is 30 inches, and each of these cuts is x. So the problem from a long time ago was, let's suppose I had this piece of cardboard, and I cut x's, squares of x out of each corner. I could fold up the sides, and it would make a box like that, right? An open box like that. Do you remember that problem? Do you recall if this is this side, and it's not scale, of course, but if this is this side, what's the length of that? Is it still 30? 30 minus x is close, but it's not 30 minus x.
30 minus 2x.
30 minus 2x, yes, because you have an x from each side. You okay with that? Follow? How much is that side? Is it still 16? Very good. Okay. How much is the height of our box? Whatever the size of the corners you cut out, that's going to give you the height. Do you follow? You're taking this square, right? You're cutting out a square. You're going to fold up this side, fold up this side. It's going to give you that box. It's going to be a height of x. Show of hands, how many feel okay with our picture? Now, what we want to do in this problem, I want us to find out the maximum volume that we can make this box. So let's say you're working for UPS, right? They say we get so much of this stuff. We have so many pieces of cardboard left over. They're 16 by 30. I want you to take a stamping machine, cut out X's, fold them up, take the sides. How many boxes can we make? Or sorry, what's the biggest size of box we can make out of this? And you go, well, I don't want to just waste product. Let me do the problem real quick. So let's figure this out. So we want to maximize the volume. Well, I've told you there's really two things we do after we draw a picture. Number one, we draw a picture. Number two, we got to find a formula. We got to find any constraints that we have. So let's work on a formula. Can you find a formula for volume? Because that's what we're trying to maximize. Say it again. So basically all three dimensions times each other, right? In our case, can you tell me more specifically what that will be for us?
30 minus 2x in parentheses.
Oh, yeah. That's important. Yeah, you should have that. And then what else?
16 minus 2x.
Times x.
I'll put the x out front. Is that okay with you? So don't forget about it. One dimension, length times width times height was going to give you the volume. You feel okay with the volume? Now let's look at a constraint. It told you nothing else about this problem. It just said, I have this, make me a box. I told you nothing else. However, inherently in this problem there is a constraint. In fact, we talked about it the first time we had this. If you watch the video, you can see it. There's a constraint here. What's the constraint?
Size of the cardboard.
Wait, why not 16? Why can't x be smaller than 16? Why is it 8?
Because you have to take it from the side.
Very good. If you didn't hear her, she said you have to take it from both sides, right? So if I make an x cut here, I have to be able to make the same x cut here, right? If I go more than 8, I've overlapped, I don't have any more stuff to cut off. So 8 is the maximum cut I can make. Would it be a good idea to cut off 8? If I cut 8 and 8 and 8 and 8, that's going to be the worst box ever. It's going to be a really small piece of cardboard. And you go, hee, and then you go, dude, seriously, you're fired. Right? That would be silly. You don't want to do that. So you could do 8. You could. But you know it has to be less than that or equal to 8. What's the smallest cut you could make?
0.
What if you didn't make one? You'd have the second worst box ever, right? The first worst box is you cut something off and fail to make a box. That's the 8 and 8. You cut off 8, you cut off 8, that's gone. You cut off 8, you cut off 8, that's gone. You basically have a 14-inch by, whatever that is, 14 by 16 flat piece of cardboard. If you don't make a cut, at least you have a 16 by 30 flat piece of cardboard, but it's still not going to hold anything. But you could check it. Understand that that is my inherent constraint. Do you see it? Okay. We have a formula. It's in terms of one variable, that's great. If we had 2 variables, we would need another constraint to work with it. We have a constraint that's going to limit our end results, that we're going to check our endpoints there. What do you do now? You're trying to maximize, right? You know maxima and minima have to occur here, here, or somewhere in somewhere in there, right? It's got to be in there. But the places where it occur are the places where the slope is going to be 0, right? How do you find the slope? Take a derivative. When all else fails, take a derivative. You going to take a derivative of this product rule? No, you're not going to do that. Why don't you distribute it out, see what you get, take a derivative, set equal to 0. So that's volume. I don't know if I did that right. Did I do that right? Did I mess it up?
Sure.
I did right?
Oh, sweet.
Seriously?
Really?
Good, because I was guessing. I was totally guessing.
Yeah, no, you did.
No, I'm just kidding. I knew it. Anyway, so you distribute it, you combine everything together. Hopefully you got that far. Did you get that far? Now take your first derivative. Make sure I'm right, by the way. I like being right. That's awesome. Sorry, that's v of x. So v prime of x is that? Yes, no? Okay, that's nasty. What do you do with that? Set equals 0 and pray you can factor out 12. Right? Set equals 0 because that's going to give you the only places where you have a critical point. Critical point is the only places you have a relative max, relative min. So set this thing equal to 0. Does 12 factor out of it?
No.
What do you do?
Try 6.
Try 6. Does 6 factor out of it?
No, you can do 4.
Do you do 4? You can't do 6? Darn it. Hate that. You can do 4? So 4 factors out of it. You can still factor out the 4 though, right? If you don't want to do quadratic formula, that's How much is that divided by 4?
46.
120? Well, you can try to factor it or use quadratic formula. Do you remember the quadratic formula?
Yeah, 9.
X equals, what? Oh, we should watch Matt C video. We even sing about it.
Minus 8.
X equals minus b plus or minus radical b squared minus 4ac all divided by 2a. Get it?
Nice. Brings back so many memories of high school. First time I've ever heard that song.
Really?
Yeah. It's my government song.
Are you working it out? Have you already worked it out? I have no idea. Those are too big for me to do in my head. I don't know. I don't know what it is. I'm gonna.
23 plus or minus
216.
Total?
Oh, no, just round, not even.
This is
2116.
2116 total.
No, 676. 676.
766. Oh, damn it.
676.
6. That's easy.
Yeah.
6. What's the square root of 676?
26.
126.
26. 126 would be huge.
Very good.
And then you get 23 plus or minus 13.
Okay, let's see. You get what?
23 plus or minus 13 over 3.
23.
And well, plus or minus 13. You divide everything by 1/2. That's where I did it.
72 over 6
12.
and 20 over 6.
Factor out of 2.
12 and 10/3 is what you're telling me?
Oh, no, answer that.
Yes, no? You feel okay with 12 and 10/3? It took way too long. OMG. BFF. TGI Fridays. Tell me something about these points. Why can't it be 12? We can't make an x big as 12. So this one, even though it says 12, You cannot do that. The only one it could possibly be is 10/3. So let's think about this. Now, realistically, we already said, and you can check it, you can check your endpoints. In fact, I'll erase this, I'll do it over here. Your endpoints are 0, 8, and the only critical number you had was 10/3. If you make 0 as your x cut, you're going to get a volume of 0. If you make 8 as your x cut, you're going to get a volume of 0. Are you with me still so far? Look at your volume function. It says if you make, let's see, make a cut of 0, 0 times anything is 0. You make a cut of 8, 16 minus 8 times 2 is 0, that's times 0. So you're going to get a volume of 0. The only one that could possibly work is 10/3. So what you would do, I'm not going to spend the time to do this, but you'd find out whatever, has anyone done that, the volume for that 10/3? If you do, what you do is you plug in your 10/3, you'd find your volume, whatever this is your maximum. So the maximum volume would be plug in 10/3 to your original volume function, figure out what it is. I'm not going to have you do that right now, do it on your own time. Figure out what that volume is, and that will be your maximum volume. It occurs at a cut of 3 1/3 inches. You follow me on that? 3 1/3 inches. How do we feel okay with our maximization so far? You ready to try something a little bit more fun? Because when are you ever going to do this in real life? Well, maybe.
Box cutter.
Yeah, I'm not a box cutter. But I do build oil pipelines in the middle of the ocean, so let's do an example like that, okay?
Wait, really?
No, I wish.
That's a summer job.
Seriously though, any questions before I erase it? Do you understand the idea? You understand how to draw a picture, come up with a formula that relates that picture to what you're trying to maximize or minimize? Do your derivative. It's all about the derivative. Set it equal to 0, solve it, come up with your constraint, and check your endpoints. That's absolute max min. That's exactly what we've done before in, what, 3 point, I don't know what it was. We've already done that. You said you plug in your endpoints, you plug in any critical numbers you had, whichever the biggest one, max. Smallest one, min. No problem. That's the idea.
726.
How much?
726.
726? Anybody else get the same answer?
I did.
726. This would be in cubic inches. You guys ever go to Santa Barbara? Ever? You ever see those oil pipelines out there? Sometimes they have pipe, let's say you want to build one of those, but you wanted to not have tankers go back and forth. So what you're going to do is build that thing and then build an under the water pipeline to land, because you have a refinery right off the coast somewhere. So here's what happened. Your refinery's here at point B. The oil you located is there. Oil. If you were to go directly from the oil to shore, we'll call that point A. Here's the idea. Here's what you know about the situation. Pipe costs a whole bunch more to put it in the ocean than it does on land. You gotta have people go out there, lay it right, go under the water, put the pipe together, do all this stuff, okay? Now we're gonna make this kind of simplified. It probably doesn't cost a dollar per kilometer, but we're gonna say it costs $1. Maybe it's like $1 million per kilometer, or $1 billion, I don't know how much it is. But let's say that it costs twice as much for the underwater stuff as it does for the on-land stuff. You with me on that? So the pipe costs $1 per kilometer in the ocean. And half of that on the land. So whatever it is, you could substitute in different numbers, and you get this right, the same exact idea, okay? on land. If we want to minimize the cost, which I hope that you do, right? You don't want to build the worst pipeline for, if you want to build the worst pipeline, you go like this. Let's put the oil way over here, and then down here, and then over here. That'd be stupid, right? We want to come up with the most cost-effective way to do this pipeline. So if we want to minimize our cost, what would you do? Would you go like this? Would you make your oil pipeline here and there? Would you do that? I don't know. It seems to me like that would be the least amount of ocean pipeline, but the most possible land pipeline, wouldn't it? I don't know if that's going to be cost effective. I have no idea. I really don't know. Would you go straight from the oil to the oil stop? You could. That would be the fastest way, right? The least amount of pipe in general. But this is the most expensive pipe you can lay, right? This would be less expensive. So chances are, we're going to come to some point that's intermediate that says, well, how can we do this? Maybe we take our oil and we pipe it to some onshore point and then lay the pipe from here to here. Does that make sense? The way, if you label it point P and you say, well, point P very well could end up being at A, right? It could be here, it could be at point B. It'll come out in the formula. It'd be at your endpoints, all right? So let's say, if we want to minimize our costs, how far should point P be from point A? Oh my gosh, I don't know. No idea. Let's try to think through this thing. Oh, there's one more thing I need you to know. Doing your measurements, that's 8 kilometers. Okay, so you know that. And you know that your oil is 5 kilometers off the shore. And those things you know. What we want to know is, where's that point got to be to make this the cheapest? So we're going to basically make it in the ocean pipeline combined with the on the land pipeline and see how far this is. What am I asking here? How far this has to be from there? What do you want to call that? The distance from here to here. I call it some variable, whatever it is. Just call it x. Now let's think critically about this. If this area, I'm sorry, this distance is x from A to P, how far is the distance from P to B? Don't use y, because then we have to come up with another formula to solve it. Try to base it on x. That's the reason I gave you the 8. X minus 8 or 8 minus x? If this distance is 8, if that was a 2, that would be a 6, right? If that was a 4, that would be a 4. You're taking 8 minus that x. So whatever that is. Okay. Do you feel okay with our picture so far? Do you understand the question? The question is, let's try to minimize our cost if we have to get oil from there to point B. If we know that this is 8 kilometers, we know that it's 5 kilometers off the shore, let's find the best place to do that so that we don't spend a whole heck of a lot more money than we need to. Well, here's the deal. We need to come up with some formula that relates the cost of this to our problem. So let's try to do that. Cost. What do you need to know to find the cost of something? Let's see. Well, we need to know how far this pipe is, don't we? Okay. I'll give you the easy one. How far is it from P to B? Would you agree that 8 minus x in parentheses, would you agree that that is the amount of on-land pipeline we're going to need? Do we need pipe from A to P? No, we're going to go from the ocean to P. We need pipe from P to B. You follow me on that? That's the 8 minus x. 8 minus x. How much is each, and that's in kilometers, 8 kilometers minus x kilometers. How much is each kilometer of pipe on land? No, it's not a dollar. It's a half of a dollar. So would you agree that if this is the amount of pipe, 1/2 of that, remember this is dollars, half a dollar times that amount is going to give us the amount of money it's going to cost to go from P to B. How many people feel okay with that so far? Okay, let's do that. Let's do oil to P. Let's do this distance. How do we do that distance? That's a right triangle. That's why, by the way, we call that x. Right, that's why. So that we get a Pythagorean theorem triangle. It's kind of nice. You don't want to do it with 8 minus x, it's crazy. So this is x, that's 5. If this is x and that's 5, this is, I'm going to kind of do it a little quickly for you. This is the square root of x squared plus 5 squared. Do you follow me on that?
Yeah.
Leg squared plus leg squared equals hypotenuse squared. Take the square root of the hypotenuse, and that's the distance from A to P. Oh, sorry, from oil to P. Yes, no? Leg squared plus leg squared is hypotenuse squared. So if our distance is, I'll put it in black so you see it. The square root of x squared plus 25, which, by the way, you can't just take the square root of x squared and the square root of 25, right? That's not just x plus 5. You can't do that. It's square root of x squared plus 25, and you can't do anything with it. Would you agree that this is how far it is from the oil to point P? Okay, so this is the distance from oil to point P. This is the distance from point P to point B. This is all the pipe that we're going to need, right? What's the cost of this pipe? $1. Could you do it with different amounts of money? Of course you could. The numbers get worse. But this is the same idea. How do I have the cost of this and the cost of that? What do I need to put between them? No, not parentheses. I need to add those costs. Let's try to think about the formula one time, then we'll start working with this next time. We're going to take our problem and break it down little by little. We're trying to come up with a formula to minimize the thing that I'm asking you for. Here we had to minimize the cost. So to find the cost out, well, you need to know how far your pipe is, multiply that by the cost. If this whole thing is 8 kilometers and A to P is x, then P to B is 8 minus x. That's the distance. Each of those kilometers costs $half. That's this portion of it. To get from the oil to point P, which is probably it's going to be some intermediary point, we're going to find the distance using Pythagorean theorem. That's the 5 squared plus x squared. Take the square root of it. That's how we get that. Each of those kilometers costs $1 each. If we have the cost for offshore plus the cost for onshore, that's our total cost. How many feel okay with this so far? All right. We're going to continue working on a problem. I'm going to kind of recap what we did last time, just so you know. So what we're doing is we're drilling for oil off of some coast somewhere. And we know where this oil is, and we know where we want the oil to be, and it's not directly out from the shore. And maybe this is too expensive to buy over here, so we got to get the oil from here to our oil stop. Maybe this is our shipping yard, or maybe it's our refinery, and we want to pipe it directly to there. You get the idea? So we know one thing about it. We know right now that it's 8 kilometers from A to B. We also knew that the oil happens to be 5 kilometers off the shore. And let me explain the idea once again. What we're trying to do is we're trying to minimize the cost of our pipeline. The pipeline costs $1 at sea. Now, of course, it's going to be more than that in real life, but the principle stays the same. And $half on land. So we had some options here. We could have made the sea line as cheap as possible. That would go directly to the shore, right? But then our land line would be as the longest possible. Maybe that's not going to minimize our cost. We could have gone directly from the oil to our oil stop, which says you don't do any land line, but you have the most expensive sea line you can possibly have, right? So we're saying, what if this is the case? Because we're not quite sure. We don't know what's going to happen. But most likely, we'll have some sea line and we'll have some land line, and that will probably minimize our cost. So we asked the question, how far does point P have to be from point A in order to minimize our cost? That's a whole lot different problem. Well, do we know how far point P has to be from point A right now? So we're going to call it X. We call it X because we don't know the distance, and if you think about it, we're going to have to figure out how far this is, right? That's going to be a Pythagorean theorem problem, which I'm seeing in my head right now. I'm thinking, you know what? I don't want to deal with something very complicated here. Let's just make it an X. So I'm going to pick X. If that's X, and we know the whole distance is 8 kilometers, then the distance from P to B is what?
8 minus 6.
Yeah. It says this. It says the distance from, the amount of pipe that we're going to have for our land is going to be 8 minus X. Whatever X is, we subtract that from 8, and that's how much pipe we have to have in the land. You follow me on this? But what we also need to know, we've got to know the distance of pipe we're going to lay at sea. So from the oil to point P, we got to know that. And I think I did this last time, but I did it very quickly. We'd use the Pythagorean theorem. It is a right triangle. So it says leg squared plus leg squared equals the hypotenuse squared. If that's true, I'm going to erase my ocean here. Ocean. If we do that, then I know whatever this distance is equal to x squared plus 5 squared. That's a leg squared plus leg squared if I take a square root of it. The reason why I got to take a square root, the hypotenuse squared equals that. So to get the hypotenuse, take a square root of both sides. So our distance here is the square root of x squared plus, let's just change it to 25. You okay with this so far? Now, before we work on the formula, I don't think I did this last time. Let's talk about a constraint. Let's talk about a constraint on x. What's the least amount of distance you could have for x? Remember, x is the distance from A to P. What's the least amount you could have? You probably wouldn't want negative, right? If you did negative, you'd go this way. Would you want to go this way? That'd be pretty stupid. Because you go, let's make our oil over here and then run it. That'd be really silly, right? We'd probably go this way, that way it's closer to our oil. So 0 is the least amount we could make x. We could go directly from oil to shore, right? 90 degree angle, directly right there. That'd be the shortest. That'd be probably the best way to go if that minimized our cost. We're not going to go this way, we go straight down. So 0 is the least we could have for x. But it could be 0. What's the greatest we could have for x? Yeah, you're not going to do this. You're going to go, ooh, let's go way past and then come back. Well, that'd be pretty stupid as well, right? You'd maximize costs, probably. Well, maximize costs would go everywhere. But you go way past and then come back. That'd be silly. So we could have 8. You'll agree that x has a minimum of 0 and a maximum of 8. Well, what that does for us, that gives us some inherent constraints, that gives us some endpoints. What this says right here is that if we have endpoints, which we do, 0 and 8, and we find a critical number, one of those points is going to minimize our cost for us. It's either going to be at 0, 8, or somewhere in between there if a critical number exists. Do you follow? Okay, so at least we have our constraints down. Now let's talk about the formula. Here's how you come up with a formula for the cost. I didn't start with this last time, but I'd like to show this to you. To find out your cost, you really just have to identify the pieces of your puzzle, the pieces of your picture in this case. You go, all right, I know you have some pipe at C, so the cost of the pipe at C plus the cost of the pipe on land. Well, since we know how much it costs per kilometer, let's just figure out the kilometers. So the pipe on the land. We just talked about this, but the pipe on the land is from P to B. That's our 8 minus x. So if we know that the distance of pipe is 8 minus x, and it costs $0.50 per kilometer, this is how many kilometers we're going to have of land pipe. We're just going to take half of that, and that's going to be the number of dollars we're going to spend for the pipe on the land. You okay with this so far? That's going to be added to the pipe at C. Now we just figured out how much pipe we have at C. It's a square root of x squared plus 25. That's how many kilometers of pipe we're going to have under the sea, or at the sea, in the sea. Each of those kilometers costs $1. So if I multiply $1 times each of those kilometers, I'll have the total cost for the pipe at sea. And that's how you figure out the cost function in terms of x, the distance that you're looking for. Raise your hand if you feel okay with that so far. I think that's where we actually left off last time. Now, what do you want to do? What do we want to do with this? Maybe before we take the derivative, make it look a little bit better, right? Probably distribute that half into that 8 minus x, because you don't want to start dealing with derivatives until it looks kind of pretty. Deal with that 1 out front, that looks nasty, so, well, it does not do anything, but it looks silly. 1 times anything is anything, so the square root of x squared plus 25. Plus, this is going to give you 4 minus x over 2, or 1/2 x if you prefer. Still okay so far? Now, that's our cost function. And that's what we're trying to minimize. Maybe do one more thing with that square root. What would you change the square root into? To the 1/2. Not negative 1/2, right? Not negative 2, but to the 1/2. If that's the function we're trying to minimize, here's what you know about maxima and minima. Absolute value, or I'm sorry, absolute maximum, absolute minimum. You know that they occur at endpoints or critical numbers. We know that for a fact, right? It's the only thing that happens with continuous functions, and that's continuous on the interval. So it's either going to be at endpoints or critical numbers. We have our endpoints, which we'll check in a while. We don't have critical numbers. How do you find critical numbers? That's where the calculus comes in for maximizing things, or minimizing things. It says, you find out what the critical numbers are. Those are the only places besides endpoints where you could possibly have an absolute max or an absolute min in our case. Do you follow me? Go ahead and take the first derivative there. What type of rule do you need to apply to take the first derivative here? General power. Okay. Did you get that far? What key piece of information have I left out so far?
The
Exponent. Don't forget the exponent. You're subtracting 1, right? You're not subtracting 1/2, you're subtracting 1. So if we take 1/2 minus 1, I need to be getting that negative 1/2. Did you get that as well? Okay. Then derivative of the inside, we know that because that is a general power rule. How about the 4?
0.
How about this? Oh, good, okay. So not another product rule or anything crazy, you just take the derivative of that little piece, that's negative 1/2. Now, this is going to equal 1/2 x squared plus 25 to the negative 1/2 times derivative
2x.
minus 1/2. Now, I know I get crazy on you guys about parentheses. I know I do. Should you have parentheses around this? No. If this had all been in parentheses, then yes, you would have, but you don't. This is minus 1/2 at the very end. You follow me on that? In this case, that says that this 1/2 and this 2, that is something that you can simplify out. Does that make sense? I'll show you in 2 steps. This will be 2x over 2 square root of x squared plus 25, true statement, minus 1/2. Yes, no? And then the 2's are gone. So the first derivative of our cost function, which we're trying to minimize in this case, is x squared plus 25 square root minus 1/2. That looks fairly nasty enough. What are you supposed to do with that thing? That's our first derivative. What does the first derivative stand for? Slope, okay. What do we do with that? Can you explain why? I know we talked about it a lot. Can you explain why we have to set our first derivative equal to 0? Why do we do that?
Because your maximum minimum is going to be wherever the slope is 0.
Very good. So we know that maximum, absolute, what he said, was absolute maximum, absolute minimum have to be at one of a couple places. First, endpoints could happen. But if they don't happen at endpoints, they will happen where we change from increasing to decreasing or decreasing to increasing. In either case, the slope will be 0 at that point. So if we set our slope equal to 0, that will solve for the only points where we could possibly change from going up to going down or going down to going up. Does that make sense? That's why we set it equal to 0. So let's do that. Oh goodness. What now? Cry. Give up. Go on spring break. Let's just leave. No, seriously, what do you do?
Conjugate.
No conjugate.
Add 1/2.
Probably add 1/2. Why add 1/2? Well, you actually have something nice here. Kind of nice. A little bit nice. Not super nice, but a little bit nice. Do you see what you have here? You have a fraction equal to a fraction, right? That's called a... Starts with a P, rhymes with or portion. Proportion. Yeah, proportion. What do you do with proportions? Oh dear me, yeah, you cross multiply. That's fine, that's great. Cross multiply them. Go dot, 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 dot. You're going to have 2x equals 1 times the square root of 25, x squared plus 25. That looks a lot better. Why does it look a lot better? You already have a square root isolated. Get rid of a square root, how do you do it? Square both sides. So let's square both sides. Don't forget that when you square both sides, you're not just squaring the x, you're squaring the 2x. Do you follow me? Square, square, gone. 4x squared equals x squared plus 25. Nothing changes. No distribution. The square and the square root, those are gone. They're inverse operator. They're inverse exponents. In fact, if you think about it, it's actually 1/2 to the second power, right? You multiply exponents and they're being raised to each other. That means 2 times 1/2 is 1. So it just disappears. It's great. What now? Solve for x. So I would probably subtract the x squared from both sides. Since there's not an x term, this is nicer. This is 3x squared equals 25. You with me? There's no nasty factoring to be done, nothing like that. Get rid of the 3. How do you get rid of the 3? When there's not an x term, this is the way you deal with quadratic. You just solve it for the x squared and take a square root of both sides. If there was an x term, you'd have to use quadratic formula, or you'd have to factor it, or complete the square. But when there's no x term, no just x to the first power term, this is nice. Divide by 3, you get x squared equals 25 over 3. Get rid of the square. Sorry, what does that again?
Square root plus
So
minus.
square root both sides. What do you need when you square root both sides?
Plus minus.
Yeah, you have to show that. So you get the square root of 25 over 3, plus or minus, of course. That's going to be plus or minus 5 over root 3. If you rationalize, multiply by root 3 over root 3, you know what rationalization is, right? You're going to get 5 root 3 over 3. Tell me something about one of these numbers.
The negative is an answer.
Say again, why is the negative not
It's not.
an answer?
It's not a constraint.
It's not in there. It's not in there at all. This is actually negative. That would be this case. That'd be going this way. We don't want to go that way. Okay? So we're not going to take the negative. So our only critical number (5 root 3 over 3). Now, do you automatically know that that's going to minimize our cost? Not really. You do have to check it. Okay, so what if we did this derivative and that actually was not this? It could very well be this, couldn't it? What if we did that? We would have just maximized our cost. Now, intuitively, we probably think that this is going to be a minimum because we're kind of thinking, this is really expensive, this is the longest distance, so it's probably somewhere in between there, but you have to check. I mean, people have made some serious mistakes by taking a derivative and not checking whether it had the minimum or the maximum. With simple formulas like this, you can think about it. But advanced formulas, oh man, you got to check. The way you check is either with a second derivative, right? Either that, and that would test concavity for you and say, oh, okay, take that point in the second derivative. If it's negative, that's a maximum. If it's positive, that's a minimum. Does that make sense? Because that will tell you concavity. Or you do the analysis that I showed you how to do. You make your first derivative test. You say increasing, decreasing, increasing. And that's going to give you what type of maximum you have. Or you check the endpoints on these intervals. So that's like 3 different ways you can check. We know that all of our possible maxes and mins have to occur here, here, or there. That's it. So if we plug in those 3 values, one of them will give us a minimum. So I'm going to go back over here. We're going to check these points. By the way, when we're checking points like this, are we using the first derivative? Are we using the original function where I'm checking absolute max and min? What am I checking? The original one, yeah, because that's telling us actually the cost, the actual cost there. So I'm looking here, right there. Are we plugging in 0? Or are we plugging in 8? Or one of them? Can you help me out with that? 0 is 9. So this was x.
8 is 9.43.
And this is our cost, right? So 0 would give us a cost of $9. $9. Now, if this is a billion, actually a billion instead of like 1, that's $9 billion. I don't know how much it is. How about 8? What'd you say, 8?
9.43.
Okay. How about 5 root 3 over 3?
Close enough.
I don't know. I don't know what 5 root 3 over 3 is. We'll have it written down. How many people got 8.33? 1, 2, 3, 4. Yes, yes, yes. And you all sure you're right? I love it. 8.33. Did we find the minimum? What is the minimum? Good. Okay, the minimum isn't 5 root 3 over 3. That's not what the minimum is. The minimum cost is actually $8.33. The maximum cost would have been $9.43. Right? This 9, it's intermediate, but it's definitely not the minimum or the maximum. So our minimum actually occurs when x equals 5 root 3 over 3. How much is 5 root 3 over 3 about? 866?
Yeah.
So about 2.9 kilometers. So here's what this says. If you're the one building this pipeline and your boss says, look, I gotta have you minimize the cost, which you could do, right? That's actually kind of a realistic example. If you had to actually do this, you could do it with this, right? You could easily do it. All you need is the cost. Now, that's not gonna be dollar, but even if it was like $1.38 million per kilometer at sea, you could do it. Cost there, you could do it. You'd say, okay, boss, whoever you are, we're going to go from point A, which is directly perpendicular to from the land to our oil. You're going to go 2.9 kilometers, and that's where you're going to draw the line. And you can say you're going to make your oil line from there to there, exactly from there to there. Make your land line from here to here. Have two people start working, meet at the middle, and that way you save the most money. Does that make sense? We definitely don't just want to guess. This right here, if x is 0, you got $9. Doesn't seem like a whole lot, but you're like, oh, that's only, what, 67 cents. But if this is in billions, that's $670 million, if I did my math right. That's a lot of money. Okay. You definitely don't want to have 8. Oh my gosh, if you did 8. That's the worst. The worst you could do is go directly from there to there. That's the worst, unless you couldn't buy all this land, and then maybe you'd have to, but that would be a different constraint. How many people understand our example here today? Good. We're going to do one more. We're going to talk about minimizing material. So this is more of a geometric approach. This had a little bit of geometry in it, but it's only Pythagorean theorem. This is actually kind of a economist or maybe a business approach. This one's definitely going to be like, I don't want to say engineering because we're not doing any engineering, but dealing with more of a geometric figure, okay? So let's suppose that you're in the business of bottling Coca-Cola or some sort of cola, and you want to come up with a can that holds the most amount of soda for the least amount of material, right? So when you see a can, typically we design cans that fit in your hand, being they're easy to drink, right? But it's probably not the most, honestly, economical way that you could package something. It's actually a little bit too long. We'd have to have something more squat to save ourselves some material. Do you follow? Would you want to make a can that's like this round and this big? Drink my soda. No, probably not. Or unless you go to the Yard House, you're probably not going to make a can that's this tall and that skinny, right? Have you ever been to the Yard House?
Yeah.
Do you know what I'm talking about? They have beer that's this big. It's a yard. Right? It's this big. It's like this big. That'd be like 2 yards. But you go like that. Okay, you're not going to do that if you want to say if you want to look cool, then yeah, of course. But if you want to save money, like with bottling, you're not going to do that. That'd be stupid. So let's talk about. We want to bottle 1,000 cubic centimeters. Not bottle, I guess can. We want to can 1,000 cubic centimeters. How much is 1,000 cubic centimeters? So what is in science? You sciencey people. Is that a liter? Is that close to?
Yeah.
That is a liter, right? Cubic centimeter is a milliliter, is that true? Oh, that's right. Yeah, we're doing right. So we want to basically can a liter of cola. Or beer, if you like beer, a beer can, I don't care. Make it exciting to you. We want to minimize the material needed to make that happen. Well, you know what? We better start with the picture, just like always with these problems. So let's start with a cola can. Hey, what are the dimensions of a can that you need to know? What shape is a can? So it's cylindrical. What dimensions do you need?
Need the radius, you need the height.
Yeah, it is circular in nature if you're looking down the top of it. So yeah, definitely have to have something to do with the radius. Also have to do with the height. For sure. So let's go ahead and do this. R is the radius. H is the height. And let's do this. Let's call S the surface area. You follow? Because the surface area is the amount of aluminum, or whatever you're going to make your can out of, hopefully probably aluminum, that you're going to need. Do you follow me on that? So surface area would be the faces, the top, the bottom, and the side of our cylinder. There's also one more thing we have. We have the V, the volume. Now before we begin, let me ask you something. What are we trying to minimize here? Are we trying to minimize the volume? Are we trying to minimize the radius, the height, or the surface area? That's what the question is asking you. It says, minimize the material. The material is the surface area, not the volume. The volume is actually constant. Do you see that? That's the 1,000. That's not going to change. We have to have it hold a liter full of soda. Because if it doesn't, you're going to have it in your mills, or your, is it a mill? A soda mill? We're going to soda plant, I don't know what they call it. But they're going to fill full of soda with a liter. It's going to either overflow or it's going to be way too small in there. So we want it to hold exactly a liter. Let's talk about our formulas. And we'll talk about any constraints we have. Let's do the formula first. The formula, if we're trying to figure out the surface area for this thing, note that what we really have you ever thought about what a cylinder is? Have you ever cut a Pepsi can apart? I am, because maybe you guys are interested to see what it actually looks like. It really is just a rectangle with two circles on the top and bottom, right? So if you did this, you took your rectangular piece of paper and you just fold it around and got this, can't fold it around very well. You got the cylinder and you just close it in with two circles, you basically have a can. Follow? So what this really looks like, if I were to disassemble this and make the individual figures, I've got the body of my cylinder, I've got a circle, and I've got a circle. Up and put the lids on, that's your can. So let's think about the surface area of this thing. What's the distance from here to here?
R.
Is it the same R as this?
Yeah.
Of course. Is this the same R as that? It's a cylinder. How far is it from here to here? From here to here. Okay. Now here's an interesting one. This is the weird one. Because we need to know that too, right? What's that? Yeah, that's the circumference of the circle. It has to wrap around the circle, right? So whatever the circle is, that's got to wrap all the way around it. That's 2 pi r. You okay with this so far?
We'll go back to geometry.
Geometry, yeah. Actually, some calculus is calculus and analytical geometry, which this would probably take part of that. But anyway, do you see the figures that we have? We get 2 of these circle guys that are exactly the same. We've got a rectangle that's 2 pi r long. That's a weird way to think of a rectangle, isn't it? The rectangle is 2 pi r long, and it's h high. So let's think of the formula for a surface area. It's got to include 2 tops plus 1, let's call it the body. Do you follow that? 2 tops. 2 times, now the top. We're talking about area, right? The area of these figures, because surface area is what we need here. So what's the area of one of the tops?
Pi r squared.
It's a circle, yeah, pi r squared. So would you agree that the two tops together are 2 times the pi r squared? Pi r squared gives you an area of a circle. We have 2 of those circles, therefore we have 2 times the pi r squared. Yes? Add to it the area of the body. Remember, this is surface area here. What's the area of our rectangle? How do you find the area of a rectangle?
Length and side.
Okay, so 2 pi r times the h is exactly right. Feel okay with this so far? You sure? How many people do feel just fine with that? It takes some work to really think about that, doesn't it? And of course, I can't give you an example for every one that you're going to have, but the idea of going through is the same. Draw a picture, come up with a formula, come up with some constraints. Now, we're done with the formula. That looks great to me. Almost great. We have too many variables. We can only have one variable for this. But we're going to have to use a constraint to make that work. So the constraint. What is the constraint?
1,000 cubic centimeters.
Sure, something has to do with 1,000 cubic centimeters. What has to do with 1,000 cubic centimeters?
Not of material.
Not the surface area.
The volume.
The surface area is the material that we need. We know nothing about the surface area. Okay, notice that you can make the surface area an infinite number of possibilities and still come up with a liter of cola. Like I said, you could have, let's see if I can do this. This as your can, which holds a liter. Right? That would be stupid, but you could do it. You could have this as your can, which holds a liter. But we want something that's going to minimize the surface area but still hold a liter. The constraint is holds a liter, holds 1,000 cubic centimeters. You follow me? So we need to come up with a volume. We also need that volume to equal 1,000 cubic centimeters. Does anyone know off the top of their head the volume of a cylinder? It's not hard to figure out if you think about it.
Pi r squared h.
Pi r squared times the height. Circles stacked up on top of each other. Yeah, very good. And we said the volume had to be what now?
1,000.
So if our volume is pi r squared h, which is the volume of a cylinder, then we have 1,000 pi r squared h. Do you feel okay with the surface area? Do you feel okay with the volume? Which one are we trying to minimize again, the volume or the surface area?
Surface area.
So this is not what we're going to take a derivative of.
Yeah.
We're going to use this as our tool. We're going to use this to solve for a variable, plug it into here, and take the derivative of this one, because this right here is the thing that's going to give us our max or our min. You right? What variable do you want to solve for? You want to solve for r or do you want to solve for h?
H.
Most definitely h. That's much easier to solve for. If you solve for r, you're taking square roots, plugging those things in over there. That'd be kind of nasty, right? So probably solve for the h. How do you solve this for h? So if we do that, we get the surface area that we're trying to minimize. 2 pi r squared, we like that. 2 pi r times h. But h is now 1,000 over pi r squared. Feel all right with this so far? Do you see why we need that substitution? Otherwise, we're not going to be able to take a derivative, at least not without using implicit, and that would be very difficult because we don't have a rate of change. And implicit is not, it's not with respect to time at all, right? So we can't use that stuff. You're thinking, why don't we do that? But it's not with respect to time. This is not changing. Okay, this is, we want to figure out the minimum surface area here. It's not a related rates problem at all. So here, well, we had to change it to one variable. We only know how to take derivatives with one variable. So we have the s equals 2 pi r squared plus, what's this going to give you?
2,000.
Great, 2,000, I see that. Pi's gone over R. Still all right? Probably do one more thing. What are we going to have to do next? What's the next idea?
Derivative.
It's a derivative. Now, our constraint didn't come up with any endpoints. You see that? We didn't have any. We can make the dimensions any way we want. So we're really going to have to take a derivative to find out the maximum in here, if we have one. So we're going to go ahead and take a derivative, but before we take a derivative, you might want to move what?
Part of the
The R. Yeah, shoot, let's take our derivative. What that's going to do is give us our slope. We know that absolute maximum and minimum, if they're going to occur here, they're going to occur at a critical number, where we're changing from increasing to decreasing, or decreasing to increasing. What did you get? Minus 2,000 what? R to the negative 2. Okay, good. I like what Michael said. He said, put it over R squared. Maybe a little bit easier to think about, right? What are you going to do with that now? That's your first derivative. What do you do? Let's do that. What now?
Solve for R.
Gotta solve for R somehow. Probably a good way to go about it, multiply both sides by R squared.
You need your minus sign.
Oh, no, I'm sorry. You know what, I left out a step. I added that. I did it all in my head, I'm sorry. It made sense to me. It's good to me. Okay, so set it equal to 0, add that over, that way you have different sides, and nothing you really do at this point. Maybe now multiply both sides by R squared, that way you're going to have R cubed, and maybe divide both sides by 4 pi. Do you see what I'm talking about?
Yeah.
So that ultimately you're going to get this. Multiply both sides by R squared, you get the R cubed, divide by 4 pi. And you get 2,000 over 4 pi. Simplify a little bit. What's 2,000 divided by 4? So then R cubed, 500 over pi. I'm not really interested in R cubed. How do you get rid of the cube? Let's take a cube root of both sides. That's great. Great idea. If you're looking for an exact answer, it's the cube root of 500 over pi. Now, if you work at Pepsi Cola, and they say, what radius do we need? And you go, cube root of 500 over pi. And you go, seriously? Can you please tell me what radius I need here? And you're going to go,
0.53.
say what now?
2.53.
2 point?
53.
Really? Maybe. Can you try that one more time?
5.42.
That's what I got.
Yeah.
5.42. 500 divided by pi, take a cube root of that, you're going to get the 5.42 what? What is it? Not cubic. That would be a volume. This is a distance. Notice what you did. You took a cube root, right? You took a cube root that has cubic centimeters. That would be centimeters, not inches. Oh goodness. We made that inch. That's a huge can. Colon.
It's like lobsters.
That's bigger than that. 5.42 centimeters. Divide that by 2.54 and you get the inches, right? So you can figure that out if you really wanted to. But that would be 5.42 centimeters, roughly. Can you tell me how you would find your height out?
Well, the animation will be solved for
It's already solved for h. You plug it in. Believe you're going to get 10.8. You try that.
Oh, no, there's no way I should remember that.
He's taught this lesson before.
Yeah, 10.8.
10.8 what?
10.8.
No, 10 point, isn't it like 10.84?
2.838.
Yeah. It's twice the radius. No, it's exactly twice the radius. Which is interesting.
It's not gonna be like that for everything.
Think about it.
What, this is weird, but what maximizes volume of a cube of a rectangular prism? If it's a cube, right? That's the least amount of surface area, the maximum amount of volume. A cylinder, if you had it the height as twice the radius, think about what that says. The radius is this distance. That means it would be the height times the height. That would basically be kind of a cylindrical version of a cube. Do you see that? That's interesting. Kind of weird. Now you could prove that it is twice the height is twice the radius. You could do that. What I want to do is more calculus. We have no way of verifying that this is actually a minimum or maximum right now, right? You're just guessing. What if you accidentally minimize that you didn't? What if you maximize the surface area? This is minimized. But how you do it, just go ahead and take another derivative here. That's going to be 4 pi 6,000 over r cubed. Did you follow me? Yes, no?
Yeah.
Are you with me that that's the second derivative? What does the second derivative give you? Okay, so plug in the r that you have. Now remember, we're not worried about the actual number. We're worried about whether this is positive or negative. So think about this. If I plug in 5.42, it will give me a concavity. True? It will either tell me concave up or concave down. It won't be, most likely it won't be an inflection point. So if this is 5.42, 5.42 cubed is, I don't care, but it's positive. 6,000 over positive is a positive. Add things together, this doesn't change, right? 4 pi is positive. Positive plus a positive is a... Would you agree that at r equals 5.42, this is concave, what is it? Up. Because this is greater than 0. So if we're concave up, and this is the point where we change increase and decrease or decrease and increase, which we actually didn't check, that would have to be this point. Right? That have to be that point. So is that an absolute minimum for us for this range? Yes. Yeah, that's a minimum. We just minimized the surface area and you proved it. The other way you prove this is you put this on your first derivative and you check 2 points, one to the left and one to the right. You check like something like 5 and 6. And you say, oh, it's decreasing, but it's increasing. That's got to be a minimum. That's the other way you can check it. How many people feel okay with our lesson? Good. Okay, yeah, my bad. This actually should be a 4,000, not a 6,000 as previously on the video. I accidentally multiplied by a 3 instead of a 2. So the -2 times the -2,000, that's what's giving you the 4,000.